In this video, we are going to talk about cables and connectors. And many people, they really focus on PCB layout, connecting chips on PCB, but sometimes they forget about connectors. So is there something really important about connectors and ground and I/O pins, Eric?
Yes, and unfortunately, the people that design the I/O pins and their layout based on the connector they're going to use usually select the connections, the pinout, based on what's convenient either in the routing or how many pins they have available in the connector without thinking about the crosstalk. And I like using the Arduino board as an example because it illustrates so many things not to do. And I mean this in the most loving way because I love the Arduino board and it has revolutionized the access, especially kids, to electronics. So it's incredibly wonderful uh, for what it does, but it most of the boards that are distributed that are the Atmega 328 microcontroller in the Arduino form factor, most of them are not designed thinking about signal integrity. They're designed as though the interconnects are transparent, and it is such a robust chip that you can probably get away in most applications without worrying about the interconnects. And so I use it as an example of what not to do, and when we improve it, how much more we can do.
Mm-hmm.
And so if you look at the pinout on a typical Arduino, I have um, a, uh, uh, a standard one over here. This is a Uno R3 form factor. You'll see you get all the digital pins on one side, and they have one ground pin. That's the return pin. And so this is the way a lot of connectors I see are designed. They have a whole bunch of digital pins that are going to carry digital signals without thinking that, oh, those digital signals have currents that are going to flow in them, and those currents need a return path. And so it's the ground pin. It's that's connected to the circuit ground of the board, which is the return pin of the digital signals. And some folks will say, well, okay, so I've got a lot of digital current. Like if I got, 10 milliamps in each digital pin that's going to drive an LED or something, and I got 10 of these, that's 100 milliamps. Maybe I should have two grounds, because of the 100 milliamps of current. And so that may be two grounds. But it's not about the DC currents. It's about the switching currents, the DI/DTs. And it's not about just adding more grounds. It's where we put them to engineer a low loop inductance and a low mutual inductance.
So can I
And so,
interrupt? Can I
yeah,
interrupt you?
yeah,
So basically, what you are saying, many people think about the signals going out of their connectors, but they completely forget that the currents they also have to go somehow back. And basically, if they have all the outputs and only one ground pins, then basically it's like they are connecting all these pins together because all the return currents from all these pins, it will only go through this one ground pin.
right. And it's even worse than that. It's really about the path the loops are taking, and the overlap of the loops.
Mm-hmm.
And so so here's the problem. With the Uno, as it's designed, we only have one return pin. And
Mm-hmm.
so I don't have a lot of options to illustrate good and bad. I just have bad. I just have the pathological case. And so when my students redesign the layout of the Uno, they build a board. And here's the example of, I'm going to turn the light off so you can see it a little bit better. They design a board that is exactly the same as the Uno. It's the same layout. They're both two layers, but they design it using best design practices. And in order to demonstrate this advantage of using multiple returns and how they are located in the connector, they design the same digital I/O pin footprint as the Uno, but in addition, they add a row of ground pins.
Mm-hmm.
So on this board, they're both two layers, but on this board, there's a continuous return plane. And I think we've talked in other videos about how the return plane in the Uno, it's not a plane, it's ground filled on the top and the bottom. So it's a terrible engineered return path. And the consequence of that is we'll see in the output noise on connectors coming off. And so for the redesigned Uno, the best case Uno, we have a ground plane on the bottom, and we have a row of pins that go into that ground plane.
Mm-hmm.
And so we have the opportunity of multiple return pin connections on the outside of the signal pins as they usually are. So we just added an extra row of grounds.
Mm-hmm.
And with that, we can demonstrate using the same method that is used in or the same pinout that's used in the Uno, the kind of I call it pathological crosstalk, worst case crosstalk, and we compare that to a couple of different configurations that we can make using some ribbon cable,
Mm-hmm.
and we can engineer a couple different options to explore the amount of crosstalk
Mm-hmm.
that we get.
So the
So,
first will
yeah,
be, for example, only one ground pin and I don't know how many outputs. And then, for example, what we can also try is to have one ground pin per every single output. Yeah. And then we
exactly,
will see, we will
exactly,
compare if there is a difference.
right. So what we're going to do first is, and I'm not going to use the Uno anymore, the commercial one, because I don't have enough options to make changes. But
Mm-hmm.
we're going to use the ones my students use, they build, that we can mimic exactly the same
Mm-hmm.
pinout as this one, and we'll do that
Mm-hmm.
first. So here we got the board, and I'll show you the micro. It's really, really simple microcode. But basically, we're going to have 6 of the digital pins that switch at the same time.
Mm-hmm.
And in order to do that, we have to use port commands, because digital write, if we tell each pin, okay, digital write, pin 13 turn on, and then digital write pin 12 turn on,
Mm-hmm.
it's sequential, it's
Mm-hmm.
not simultaneous. And we want to see what the noise looks like when edges are
Mm-hmm.
aligned. And so we're going to use port commands. So we're going to turn on 6 pins, and we're going to use a 7th pin. This is my trick that I use a lot to look at crosstalk. Because, if I look at one of the pins that's switching, which is perfectly fine, and we'll do that, it's hard to tell what is the signal that I want to switch and what is the noise on top of it.
Mm-hmm.
And so we're going to look at a 7th pin that I've written the microcode to be a digital low.
Mm-hmm.
That means normally it should have 0 volts on it,
Mm-hmm.
unless, and so anything other than 0 is going to be noise.
Mm-hmm.
And so it's really easy to see the contribution of noise on it.
Mm-hmm.
So let me show you the microcode just real quick. And let's see.
Okay, so 6 of them will be switching all at the same time, and then 7th one is always, it's supposed to be
Right.
always 0.
Right. And so here's can you see the microcode on the
Yes, I can
screen?
see it.
Okay. It doesn't get much simpler than this.
Mm-hmm.
I mean, all I'm doing is I'm setting up the bank of digital I/O that are
Mm-hmm.
starting at pin 13 down to pin 6 or 7, I guess. I'm setting them up to be outputs. That's
Mm-hmm.
what the DDR-B is. It's bank B or port B. And then pin 7, I'm setting that up as our quiet low.
Mm-hmm.
So I'm saying, okay, that's going to be an output, and it's always going to be low.
Mm-hmm.
And so normally no voltage on there. Whereas for the other pins, I'm going to toggle them off and on.
Mm-hmm.
And so this is all the setup. And then in the loop, I'm going to take those digital pins, 13 through 8, and I'm going to turn them all on. I'm going to wait 4 microseconds, and then I'm going to turn them all off.
Mm-hmm.
I'm going to wait for it, and I'm going to do it over again. So they're just going to be square waves coming out
Mm-hmm.
with 4 microsecond on and off. So it's like 8 to 10. There's a little bit of delay in there because of the loop. Maybe about 8 to 10 microseconds as the period. And if it's 10 microseconds as the period, that means it's about 100 kilohertz. So we're going to see a square wave coming off when we look at one of the pins. And while they're switching, all 6 of those IOs are switching, we're going to look at the one that's quite low, and we should see nominally 0. Anything that we're going to see there is crosstalk.
Nice. Mm-hmm.
Okay, so that's the setup. So I'm going to move that here.
I'm
Um,
curious. I'm curious how high it will be.
okay, and now here's the other thing. Okay, any questions about the microcode?
No, no, no.
Okay, so here are my digital pins on my student's board, and we've got here's pin 13, and here's down 6. Here's pin 7, which is going to be the quiet low,
Mm-hmm.
and I've got the oh, I should plug it in, I guess. But before we do that, and I've got a little daughter board over here because I want to get some current switching to
Mm-hmm.
illustrate this idea. And so I have a little daughter board over here that's also two-layer board. I've got pins over here that go to LEDs
Mm-hmm.
and resistors, so I can draw some current. They go to the ground plane in the board. Now, here's where you got to keep in mind ground. It's circuit, there's local circuit ground on the Arduino board, there's local circuit ground here. If I don't connect them together, they're floating with respect to each other. And so I'm going to disconnect the ground so we can see what happens. Um, and and so these two boards are isolated from each other, but I have ribbon cable connecting basically 7 digital pins.
Mm-hmm.
6 are going to switch, the 7th is going to be low, they're going to drive LEDs, go to the ground plane, but there's no return path for the digital pins right now, and so they're not going to turn on. So I'm gonna plug in my student's Arduino board here. There we go, it's plugged in. And the digital I/O are switching. You can't really see them switching, of course, but they're switching. They're going through this ribbon cable. Let's see if I can get the camera up a little bit more. Okay, and maybe we'll move it like that. I want to be sure we see the cable there. Okay, so we have the 6-pin switching. We have the 7th one over here. It's quite low, but the LEDs, they're not on over here because there's no return path. And so I'm going to connect the ground plane, which is local circuit ground on this
Mm-hmm.
board, the daughter board, to the local circuit ground on the Arduino board. And now we're going to have current flow between the digital pin, the ground plane, returning back through the ground wire and making its way to the circuit ground on the Arduino board. So I'm going to just pick one of these guys, and we should see the LEDs turn on. And let's see. And there we go. So we've now completed the circuit basically for DC. And what we're going to do is we've got these switching. We're going to look at the switching signal first. And so I've pulled off, and it's really hard to see because they're so bright over here, but I've pulled off the pin 13 so we can sample it and see that signal coming out. And we're going to look at that with the scope. We'll use that to trigger the scope. And then we'll look at the quiet low noise over here on the daughter board, and that'll tell us how much noise that we're picking up because of the connectivity, and then we'll play around with the connections.
Okay.
Okay, so here is, I'm coming over here with a scope probe, and we're going to look on the daughter card at pin 13, and that we should see that 100 kilohertz square wave. So I've got
Okay.
him plugged in here. And yeah, let's see if that works. Okay, and so I'm going to adjust the scope here a little bit so we can see that. So you can see there's our square wave.
Mm-hmm.
And just to give you a little bit of reference here, let's see. So we're at 2 microseconds of division. So here is the start. Here's 1. Here's the next cycle. So it's 1, 2, 3, and that is 6 microseconds. So we're starting at every 6 microseconds, and and let's see, so 6 micro, that's about 160 kilohertz is the frequency. And here is the turning on, here it turns off. We wait, so we put a delay of 4 microseconds, but really it's going to do, some, it can't, it's going to have some variation of that. And it's really
Mm-hmm.
about 3 microseconds, the delay. And that's why we got 6 microseconds as the period. And so this is pin 13. Now, the vertical scale is, here it is. In fact, I'm gonna adjust the voltage scale so they're both on the same scale, both channels. So here is the vertical scale, and it's not 5 volts. I mean, it's a 5-volt power system, but my I/O is not 5 volts. Any guesses how come it's not 5 volts coming out? How
Mm,
come it's only 4 volts? So it's very subtle. It has to do with the fact that we're driving a lot of current on this little daughter board here. We've got 50 ohms and 6 LEDs. So, I mean, there's about 2-volt drop across the LEDs. So that's about 2 volts across 50 ohms. So we're talking about 40 milliamps. So each LED, we've got about 40 milliamps of current in him. And we got 6 of them that are turning on. 1, 2, 3, 4, 5, 6 LEDs that are turning on. That's 240 milliamps. For an Arduino, a 328 microcontroller, that's a lot of current. And so given that much current, we have IR drop on the output of the VCC and the output of the drivers. And we have almost a volt of IR. When we have 200 milliamps of current, we have a volt of IR drop. That's a lot. But that's why we only have 4 volts coming out. But it's still, pretty good digital signal to work in every application. So now that's what the clock is doing. That's what these IOs are doing. I've got 6 of them that are switching like this, that are going from 0 to 4 volts. Let's see while we're here, what's the rise time? And so, it's a little screwed up here because I've got all this current drawing, and the transistor, when it turns on, is a little, and the noise on it is kind of turning the transistor off a little bit. But this is what, 100 nanoseconds of division. That turn on is about less than 5 nanoseconds, and then I get this long rising edge, and this structure is all because I'm drawing so much current so fast, and I've got so much noise that I'm literally the early part of this, the fast turn on time. Let me see if I can get the trigger a little more stable there. This fast rise time, this is at 5 nanoseconds of division. So this part here is like 2 nanoseconds or so. That's the transistors turning on. This is, the voltage noise has gotten so big, I've dropped the voltage on the transistor outputs, the CMOS MOSFETs on the output, and they're slowing down now because their voltage is so low. And it takes them a while to turn on. So it's a complicated behavior of that rising edge because of the voltage drop on this rail, because of all these current switching and the impact that's having on the output transistors. But it's still pretty fast initially, and then it's taken 100 nanoseconds to get fully up to the final voltage. Okay, so that's the rising edge, and uh, and so we want to look at the noise on the quiet line while it's turning on and turning off. Okay.
Okay.
And so now I'm going to use channel 2. That's the red trace. I'm going to use channel 2, and I'm going to look at the quiet line so the wiring here, if you can see, I've got 6 of the signal pins coming out on the ribbon cable. I've got a long loopy ground wire over here. That's the ground connection. And I have the quiet line also on a long loopy wire, and this is the quiet line. And now I'm going to look at the noise on the quiet line. So let me get in here, and here it is on channel 2. And so I've triggered the scope on the IO that are switching. They're all switching at the same time. And while they're switching, this is the voltage on the quiet line. Now, nominally, the voltage on the quiet line should be 0, right? Because it's a quiet line. I'm outputting a low. And normally it is. It's pretty darn close to 0 most of the time, except when I have the DIDT when I'm turning on. So when I'm turning on, I get a huge amount of DIDT, and look at what's happening. To zoom in here on the leading edge. Look at the voltage noise on the quiet line. It's supposed to be 0, but and they're on the same scale. So if I click over here, I don't know if you can see the
No,
scale
no,
here,
no.
but they're on the same scale. They're 2 volts per division. So here's 0, here's -2, here's -4 volts. I got like almost -4 volts of noise on the quiet line. That's, first of all, it's negative. That's huge. That's a huge amount of noise on this poor little quiet line sitting there minding his own business. And now let's look on the other line. Let's look at when this is on, when all the IOs turn on. So we get a DIDT going one way. We're getting the voltage induced in the opposite direction. Now let's look at the falling edge. So I'm going to change the trigger. I'm going to adjust that to the falling edge. So now we're looking at the signal switching on the falling edge. So you can see here's the whole thing. Now we're zooming in on the falling edge, and you can see, oh my gosh, that is one distorted signal. It should be just coming down, and yet it's got this long decay, and then all this stuff here and this ringing. Let me get it a little more stable here for us. And oh my gosh, that's going all over the place. And um, And in addition, remember the red, that is the voltage on the quiet line. It is sitting there minding its own business, not doing anything. And look what happened to it. Look at this behavior. The quiet line turned off. It's got this screwy behavior because of all the voltage noise on it when it's turning off. And look at the noise on the quiet line. It goes up to 4 volts. If you had a control line that was listening to pin 7 and saying, okay, I'm going to sit here until I get the signal to turn the motor on,
Mm-hmm.
then you're going to, when all the other digital pins switch, you're going to get enough voltage on pin 7 in order to turn that motor on.
Mm-hmm.
It's going to see, yep, I went to a high, even though it was all noise. So in this configuration, the Atmega 328 has a pretty healthy rise time. It's like we saw like 2 to 3 nanosecond is the rise time of the signals coming off. The clock frequency may be 16 megahertz. It may have 60 nanosecond or 70 nanosecond is the period of the clock, but that rise time is a couple nanoseconds. And it's that DIDT during that rising edge that generates the DIDT times the inductance is the voltage noise. And so we can get pretty healthy amounts of voltage noise in the 328.
Mm-hmm.
And that's what we see here on the quiet line.
So
We're seeing
basically,
4 volts. Yeah.
so basically, if someone is connecting a different board through cable like this, and they have like, I don't know, 7 or 6 output pins and one ground, then what the other board is seeing can be complete mess.
Yeah. And so if you think about it, so here are 2 boards. Here's the daughter board. The daughter board is floating in the sense that, when I'm not, right now I'm connecting the scope probes onto the board, and the scope probe, the ground of the scope probe is connected to the chassis ground of the scope, and the chassis ground is connected to earth ground. And so by my scope probes, I am connecting the circuit ground of my daughter card to earth ground. But if I didn't have the scope probes in there, the circuit ground of my daughter card would float. And I would be connecting the circuit ground, the local circuit ground of my floating daughter card. I would be connecting that to the circuit ground of my controller
Mm-hmm.
board through the ground lead of the cable.
Mm-hmm.
And I would have this voltage that we're looking at here, that's on the quiet low, that is literally the voltage noise between the quiet low pin and the circuit ground on the board. That means that the ground wire that is connecting between the local ground of my Uno board, the microcontroller board, and the local ground of my daughter card here, that this ground wire here has a 4-volt switching noise voltage across it.
Mm-hmm.
And I'm going to get all of that DIDT from the signal pins. They're going to be switching through this wire. That means the local ground of my daughter card is switching up and down 4 volts relative to the circuit ground of my microcontroller board. And when you have a large area of metal, I mean, the ground plane on the daughter card is, a couple inches square. That is all, oops, I just disconnected my signal here. That is all switching, and I'm getting this voltage noise on it that switches with this very fast rise time compared to the local ground on this board. When you have 2 boards with different planes that have a transient voltage between them, and they're switching, those voltages are going back and forth, that means you're going to have radiant emissions. Absolutely guaranteed. If this was a system that I was shipping, it would fail an FCC
Mm-hmm.
certification test. Absolutely guaranteed. And in addition to all the noise that would be on the daughter card. And it's all because of the connectors. That it's because of the fact that I only have this one ground wire that is the return pin that's connecting all these signals. So I call this pathological. This is the worst thing you can possibly do to show a terrible problem that you never want to do this. And unfortunately, if your connector was designed like, and I mean it in the most loving way, but if it was designed like we do in the Arduino Uno boards, the commercial boards, with only one return pin and a whole bunch of digital pins IOs, this is exactly what you would see.
Mm-hmm.
You would have this problem. So that's something that it's a limitation of the board because of the way the connector is designed. There are
So
other issues, but
how
that's
can we
because
fix this? I need
how can
to
we fix this?
argue because we don't have much time. I would like to
Okay,
see the results.
okay. So here's how we're going to fix this. And I'm just going to show you the best case. And so
Okay.
what we're going to do is we're going to, instead of using the 7 signal pins with 1 return, I'm going to build this ribbon cable here, and I'm going to use every other wire as a ground wire because I can do that because I have all these ground return pins over here. And we're going to connect this up again, but we're going to do it with the right way. Every other wire is going to be ground. That means it's the return for the digital pin. And so we're going to keep all those return connections really close together. And oops, we're going to keep those digital return pins really close together. So the mutual inductance between a signal and return loop, that mutual inductance signal and return loop, is going to be really small. And we won't have so much we'll still have crosstalk, but it won't be as much in this path. And so
Can we
I'm going to
take screenshot of this so we can compare it then?
Sure. In fact, I'm not even sure we're going to need a screenshot because it's such a big difference. But let's do that. So this is the falling edge. So we'll record the falling edge
Okay.
because both are, a lot of noise, right? Okay. So here's what we're going to do. We're going to save the waveform, and we're going to save both to memory. We're going to save C1. That's the edge switching. We'll put that in memory 1, and we'll put C2 into memory 2. Okay, and then let's see, memory 1 is, we'll move them. I have them saved off screen.
Okay.
If I move them onto the screen, they're just going to superimpose, so you don't
Yeah,
see
yeah.
much. So
Okay, I
I'm going to
understand.
save them off screen here so we can bring them back
Okay.
and compare them. Now I'm going to reconfigure the ribbon cable so we can do every other one as ground.
Okay.
Okay. Now I'm going to turn my light on here and let's see if, okay. So now I can kind of see what I'm doing. Is that still a good picture for you?
Yeah, yeah.
Okay, so I'm going to turn everybody off. I'm going to reconfigure the wire, and then we're going to connect them up the right way, and we'll see what happens to the noise. So there is one digital 1, and there is his ground. Here is this guy's digital signal, and here is the adjacent ground. Here is this guy's digital signal, and here is the adjacent ground. Oops, come on.
I would like to point
Okay.
out there are
Yeah.
actually some connectors, board-to-board connectors, with ground plane. So this is exactly
Yes.
why and when this can be useful. So
Even better.
yeah.
Yeah. I think it's the old M-bus. Used to have signal pins all in a row, but it would have a ground paddle in the connector. Great connector design because that carries that return plane and the return currents all kind of separate themselves in there and you get low crosstalk. Okay, we got that one there. And now the last one over here. Okay. And okay, there we go. So we've got one N in, and so if you look close, you can see we've got a row of signal pins and a row of ground pins interleaved in the ribbon cable. Now, I have to be really careful to make sure I get the right digital pins in the right place. So let's see. So when I come over here, the white, the first one over here, this is a digital pin. So let me go here to here. And I just want to check and make sure. So I'm gonna plug in, just make sure I got it right.
Yeah, yeah.
It should turn on one LED. So let's see. There we go. Okay, good deal.
Okay.
Okay, so I get it right. So I'm gonna get the rest of the wiring going here. And
This is called experience.
yes,
Before
and this is
before
called
connecting everything, check and then
yes,
do the rest.
and I tell my students, an expert is someone who's made all the mistakes possible, and I'm well on my way to becoming an expert. And so I always like to check myself we call these consistency tests. At every opportunity, you want to be thinking about every consistency test you can. And every one you do, and you get the answer you expect, adds to your confidence. And let's see. I'm just gonna, before I get too far, let's just check and make sure I've got all these others that are doing grounds correctly. Okay, and yep, I got those that are lit up. So let me do the rest of these. Let's see. So I have digital. Let's see who's digital here. Uh, yeah, okay, so he is, okay, so he's digital, and the next one is ground. Okay, and then the white one, that's digital.
I have maybe a weird question. What would
Yeah,
when you were talking about this uh, ground connection through your scope,
yeah,
what would happen if you connect your scope through a transformer?
right. So if I were to DC isolate, sometimes called galvanically isolate my earth ground of the scope from the board, um, then uh, 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 I will um, the measurements won't change um, uh, because I'm going to be looking at the kind of effectively a differential voltage measurement on the board between the let's see here. Can I get that focus in there? I'll be looking at a differential measurement on the board, and that'll translate to a differential measurement on the other side of the transformer,
Mm-hmm.
but one side is going to be earth ground, and so it'll be voltage with respect to the other side. So it's still, it's one way of doing it. I won't see any difference because the Arduino board, my board over here, the microcontroller board, it was isolated from earth ground as well because I had it plugged into a transformer isolated
Mm-hmm.
power supply.
Mm-hmm.
And so the only connection between my two boards, the only connection between the two boards and earth ground was literally through the shield of the cable
Mm-hmm.
of the
Mm-hmm.
scope probe.
Mm-hmm.
So I would have gotten exactly the same results.
Mm-hmm. Okay.
Okay, so I think I have everybody connected up the way I want. So you can see the connections. We got a row of grounds, we got a row of signals. When I plug it in, it'll turn on the microcontroller board, and we'll get our, maybe I'll hold it like this, maybe. We'll get our LEDs turning on, and we'll start measuring those the same quiet low signals. So let me turn on my microcontroller board. Okay. And then all my LEDs are on. That's a good sign. And now, let me see, I move it over here. Now let's look at pin 13. So here is my scope probe, and I'm going to probe pin 13. And so we should see nice digital signal coming up here.
Mm-hmm.
Okay. Now, just for reference, so that's the falling edge. Let
Mm-hmm.
me just give you orientation here. So um, I'm gonna zoom in here. Here is this guy here, and I apologize, the connection's not great here because it's on its side. Um, but you can see that, hey, it's the nice square wave, right? And it's the same thing that we were seeing before, only I'm triggering on the falling edge now. And if we zoom in, here is, it's still distorted. It's not the best falling edge I've seen, but now let's compare that to what we saw before.
Mm-hmm.
So here is what we had before. Now I want to make
Mm-hmm.
sure they're on the same time scale. So let me see. So this is 100 nanoseconds. That's 100 nanoseconds. Okay, so there, you can't see it too, well, maybe you can see it. Um, I'm on 100 nanoseconds per division, and the memory is also, oops, I
It moved.
see that's the problem. It's on its side, so it's not making a very good connection here, so it just fell out. So let me get it back in there. Okay, there we go. And so now you can see, and let's see if I can toggle them. So I'm going to move this off. This is what we have now. This is what we had before. And you can see that much shorter rise. And we still have ringing. It's still distorted. We still have crosstalk, but less than we had before. Now let's look at the noise. So let me grab, here's the second channel, and now I'm going to have to do a little surgery here to get this in here. And now we're going to look at the quiet low. Oh,
Oh,
sorry, it's a little hard here in this orientation. Let's see what we can do. Okay, now maybe oh, come on. I'm gonna have to hold them vertically to get
yeah, you can do that.
the probes in here. Okay, so here's this guy, and let's see. Okay, there's our signal, and now here is our noise on the quiet line. Okay, so now just so you can see it a little, I'm going to move, now we know what the signal looks like. I'm going to move them over to the other side. And then let's look at what we had before. So here's the noise that we had before, and it was so big that it turned off the I/O, and it's the same voltage scale. They're both on 2 volts a division. We still have noise on the quiet line because we get a lot of current switching, but it is dramatically less. And in fact, here all I'm doing is making sure I'm getting my ground pins plugged in. I didn't have them all plugged in here, so I'm just getting them all plugged in. There we go. One of them popped out. So I just got them plugged in there, and now you can see that's a pretty dramatic reduction in the noise. I'm going to move them. Let's see if I can fit them if I do a 1 volt per division scale. So let's see. Yeah, okay, that one's on 1 volt per division. This one's on 1 volt per division. So now you can see a pretty dramatic reduction in the crosstalk. Hey, it's still crosstalk. It's still a crappy connection. You don't want to necessarily use, ribbon cable to transmit your signals. But if you're going to use ribbon cable, and then you better interleave the ground pins. And our noise is reduced to about 1 volt. Still a lot, but it had been so large it turned off the IOs before. And this is with a rise time that's a lot shorter. So remember, I'm going to move the other guys off to the side so they're out of the way. On the 100 nanosecond per division scale, this is the signal that was turning off when all of them switched. And there was a long rise time with that. So with the longer rise time, we also have more DIDT noise, even though the DIDT was smaller. Now, when we have less noise, the transistors are turning off faster, the DIDT is larger, and we have a significantly lower amount of crosstalk noise. So it's larger than what you see on the, what is it? The thing is, the effect is larger than what appears in the mirror. Now, this is the falling edge. Let's look at the rising edge. And to do that, I'm going to go to the trigger here. I'm going to do the rising edge, and I got to get rid of the saved stuff so they're out of the way. So now you can see it really nice. And I apologize, I didn't save the signal we had, but you remember it's like 3 volts, almost 4 volts, a lot of noise. This is on the rising edge. Here's one of the signals switching, and we've got 6 of them switching. And here's the noise on the quiet line. Dramatic reduction in that noise.
Is it same scale,
Yeah,
or it's one
yeah.
1
Oh,
volt?
no, I'm sorry. Good question. So let me put them on the same scale. So now they're on the same scale, 2 volts per division. So dramatic reduction in the amount of noise that we see on the quiet line compared to 1 ground return in the ribbon cable. And so this is just an example of, we looked at the pathological case where we had, oh my gosh, 1 return and all these 6 IOs that were switching. Here we have interleaved returns to dramatically reduce the line-to-line crosstalk.
Can we try
Yeah,
disconnecting ground pins one by one?
sure. Okay,
Do it for the
so
falling edge, because falling edge is more interesting.
okay, you like the falling edge?
Yeah.
Okay, so here's what I'm going to do here. Let me see how I'm going to do this. So I'm going to, we'll turn on the falling edge and make that falling edge. Okay, so there's the live measurement.
Okay.
And let's see if I can do this. I'm gonna leave my daughter card is a little more unstable
Mm-hmm.
mechanically, so I'm going to leave that, and I'm going to try to disconnect on the uh, on the um, the main board here. So I'm going to take one off. I'm
Okay.
going to take another one off. Can you see it
Okay.
increasing on your screen?
Yes.
Can you see that increasing? Here's another one. Just turned it off. I should have saved with a good one. I'm going to take another one off. Can you see it increasing? They're on the same voltage scale. I'm going to take another one off. And
Now
you
it's
can
bad.
see
Yeah.
as well, they're all bad. When I should have saved it.
But you still have like 2 or 3 pins connected, and it's
Yeah,
it's already like
yeah,
as
yeah.
bad as one.
And yeah, because remember, I don't know if you can see it here, but it's
Yes.
this pin over here that's the quiet pin.
Mm-hmm.
He's got 1, 2, 3 pins next to him that are switching, whose
Mm-hmm.
returns are way over on the other side. And so
Oh, try
we've
to do
already
it
got a
from
lot
the
of
other
mutual
side. Connect
inductance.
them back and try to
Oh,
do
you
it
want,
from other. Yeah.
oh my
You
gosh.
know,
Here,
when we have it connected, I'm just curious.
yeah, okay, sure. And you know what? That's what I love about these kinds of systems that I have to get the order right here. That it's flexible enough that you can do these what if experiments. And so when we do circuit board design, I first recommend my students design their prototype in I have to see what I'm doing here. I recommend they design their circuit in solderless breadboard first so that they can make these kinds of changes really easily, understanding what they're doing. And then they're in a better position to figure out what they want to do in their circuit board. Um, and you want to, if you're experimenting and trying things, you want to have flexibility to be able to do these kinds of quick experiments. Let's see, you got that one there. Okay. Well, you can see in real time as I'm
Mm.
adding these, what's happening to the noise. Come on. Okay.
Okay.
And so we've got all these in, and now I'm going to save. This is the noise. Can you see that on your
Yes, yes,
screen?
I can see it.
Okay, so that's the noise on the quiet line. So I'm going to save him. So I'm going to save waveform. That's channel 2. I'm going to save him in memory 3. Okay, so I'm going to take out first one ground.
But from the other end now.
Yeah, from the other
Okay.
end. So
Mm.
up. Yeah, see there it came off.
So not big change.
Not a big change. Oh, come on. Oh, wrong one. That was my problem. Got to get the right one in here.
So this is
Okay.
basically telling us it's important to have the ground close to the pin.
Well, that's your quiet line, but we're only looking at one. It's the others that
Yeah,
have
I
the
know, I
noise. And
know,
so
I know.
you're right. You wanna get it on uh each one, but if there's one in particular you care about, yeah, you want to put ground near him.
Yeah.
Okay, now I'm gonna here's the second one I'm pulling out.
Mm-hmm. Mm-hmm.
Here's the third one
Mm-hmm.
that I'm pulling out. Here's the fourth one I'm pulling out.
Mm-hmm. And before, when you pulled out 4, it was already
Oh
as
yeah, you
bad.
saw a big
Mm-hmm.
impact initially, right? Now, what you're not seeing is the rise time of the falling fall time of that edge is increasing.
It is, yeah,
And that
yeah.
means my DIDT is getting is getting smaller, and so that's going to give us less noise. And in fact, it's not increasing very much, but the because the others are being affected, that falling edge is getting longer, and so even though it's not increasing the crosstalk on the quiet line very much, it's because part of it is because the rise time is getting longer.
Mm-hmm.
Let me take out the next one. Oh, now we're starting to see. So I have 2 returns connected. The
Mm-hmm.
one that is adjacent to the quiet line and
Mm-hmm.
the one next to it. If I get rid of that last one here, okay, now I have one return
Mm-hmm.
connecting the 2 boards, and that return is, um, oops,
Yeah, it disconnected again. But yeah, I saw
there
it.
we go. Okay, yeah, let me get him back in.
That's very interesting.
Yeah, okay, I got that one in there, and I got that one in there. Yeah. So, and now I have one, and the noise has gotten significantly bigger. So, yeah, you want to interleave the returns, and and more is better. And I always get the question, well, how many do I need? And the answer is, my old buddy Frank Schoenig, he used to say, a lot is good. Um, so he'd say, a lot is good, more is better, and too many is just right. And that's the same guidelines for returns, that you can never have. It's like when you get old, you realize that you can never have too many napkins or too many ground pins in a connector. And at a minimum, if you can, you want to engineer every signal gets its own return.
Mm-hmm.
That is going to be anything else is a compromise. If you can't do every signal with its own return, then if you don't put in the numbers to estimate how much crosstalk you're going to have, there's no real way of knowing.
Mm-hmm.
It's about risk.
Mm-hmm.
How lucky do you feel? So I always say, when you're designing, you always want to use continuous return planes, and you want to use a return pin for every signal pin.
Mm-hmm.
Likewise, a return via for every signal via.
Mm-hmm.
Anything else is going to be a compromise. You don't know how much you can compromise, how many signals can share return, unless you put in the numbers, and that's a little bit more complicated process.
Mm-hmm. So basically, when someone is designing connector and they need to connect, I don't know, let's say 18 pins, it doesn't mean they should use 20-pin connector. Maybe they would like
Right,
to put
very
that
good. Yeah,
more grounds.
yeah. If you can afford it, you want to use you know, twice as many signal. If it's 8 signals or 18 signals, you want to have 18 returns if you can afford it.
Yeah.
And if you can't, then you have to put in the numbers.
Mm-hmm.
You have to estimate, or and there are simple ways of estimating loop inductance and loop mutual inductance, and given the DIDT. And that's why you always want to increase the rise time of signals as much as you can, consistent with your timing budget. That will
Mm-hmm.
also reduce the switching noise that we see.
Mm-hmm. And with this
Or
last
yeah,
experiment, we could nicely see that maybe we can have ground pin and then maybe three output pins and then ground pin again. It still will be
yep,
super helpful comparing to having ground pin and then 7 pins. That's bad.
yep, right. It's all a question of, is it good enough?
Yeah.
And it's really hard to estimate that. It's easily, you definitely want to estimate it with pencil and paper. There are tools that can be used to calculate it. And then sometimes it's about building a prototype and measuring it. But if it's really important, it's worth the investment to do the
Mm-hmm.
estimate if you can't afford otherwise.
Mm-hmm. Thank you so much, Eric, for this.
Okay.
It was very interesting. It was very interesting.
Yeah, and this is a really good example again of what we try to illustrate in our classes about based on the principles, what best design practices are. And then if you understand the principle and the root cause of the problem, you can turn the knob the other way and really screw it up and look at the pathological case. And that really helps to illustrate the best design practices.
Okay, thank you so much, Eric. We don't have much time for
Okay,
today, so I don't want to take your time. So
okay.
thank you.
Hey, great chatting again.
Thank
Talk to you
you.
soon.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.